Hello and welcome to Physics for Play. In this video, we're going to show you how to set up the system of equations in Mathematica to solve three-dimensional physics problems. And we're also going to solve the anharmonic oscillator using the numerical differential equation solver DSolve. Let's get started. We're going to start today by looking at the linear harmonic oscillator, which we've done many times before. But we're actually going to look at it in three dimensions, since I don't think that's something we've really showed you how to do yet. But it's pretty straightforward. So let me go ahead and quit my kernel just to make sure we're starting on even footing here. It's basically just a few steps like we've done with any of these problems. We're going to define our parameters. So we'll define the spring constant and the mass. We're also going to define a position vector and a velocity vector along with a force vector. And I'll keep things simple here. So your position vector, to define that, you're going to give it a list. So lists have curly brackets, and you're going to have it be a list of the x of t function, y of t function, and the z of t function. And make sure you use a delayed equals on that. So that's a colon equals here. And then the same thing for the velocity, except you're going to be plugging in x prime, y prime, and z prime. The force can then be written as a function of the position and the velocity. And then after you have defined these, so here we have a Hooke's law force. We wrote x of t before, but now we're doing a three-dimensional spring, so we're going to imagine that any displacement in any of these directions will experience a restoring force. That'll just be given by minus k times the displacement. Once we have these, we can solve our differential equation over some range of time. We're going to use DSolve here mostly because I'm going to be copying and pasting this when we get to the nonlinear harmonic oscillator, so we will need to solve it numerically. But we can just write we can write out the equations of motion for each of the three directions. So for x prime, we'll have mx double dot equals, double equals here, the force as a function of r and v. And since it's the x component, we want the first component of that. So I have this double bracket 1 there. And then we'll do the same for each component. So it'll be m y double prime of t equals, make sure you use double equals, force, and then in double brackets 2. So the double brackets is what you use to pull a value out of a list. So this will give me the second component of the force. And then same thing for the z component, except we'll use the third component of the force. Here I will also specify the initial positions for x, y, and z. So this is x at 0, y at 0, and z at 0. And then similarly, the initial velocities, x prime at 0, the initial x velocity, y prime at t equals 0, and z prime at t equals 0. We're going to be solving for three functions now, so I need to give it a list of x, y, and z, and I need to tell it what range over which I want to solve the differential equation. So we've already gone over how to make this graphic and animate it many times, so I'm not going to spend the time going through that code. We're just going to evaluate it, plugging in our solution, and we'll plot the results as well. And you can see we've got nothing new that we haven't seen before. We've got our mass on a spring, and if we plot it, we just get simple harmonic motion. For simulating an anharmonic motion, we're going to use the example of a diatomic molecule. So this is a molecule with two atoms in it. And we are going to model that vibration between those two atoms. We're going to model the molecular bond as a spring, but it's not going to be a harmonic spring. It's going to be a Lennard-Jones spring. So we saw before that the Lennard-Jones potential looks like this. You can go back to the second Taylor series video if you'd like to see that. We also have that we could model this as a harmonic approximation, but that the Lennard-Jones version is actually quite a bit more realistic and representative of what the physical system is like. So we're going to model it using the Lennard-Jones potential to give us an anharmonic potential. Just as we did for the harmonic oscillator a few minutes ago, we're going to follow the exact same steps. We're going to define parameters, define the force on the particle, solve the differential equation, and then set up some graphics so that it looks nice. So scrolling down, we're going to define our parameters. We've got, if you will recall, the Lennard-Jones potential has a bond strength, a symbol for the bond strength that's given by epsilon. We're just going to set that equal to 1. It also has a symbol for the bond length that is going to be sigma. And if you recall that when you when we set sigma equal to 1 in the last video, you got you had a rest bond length that was equal to 2 to the 1/6 power. So I'm just going to scale that out. And the reason I'm doing that is I want to give it a rest length, a bond length of 1. And I will give the mass a value of 1. This was just copied from above. We're just going to create a vector for the position, a vector for the velocity. We will then take the Lennard-Jones force, which I believe we computed in the Taylor series video. So I'm not going to do that here, but we'll leave it as a home exercise. All you have to do is take minus the derivative of the potential and you get your Lennard-Jones force. So we've defined the force on our particle. We're going to solve the differential equation. We do have to plug in our values. Mass times acceleration equals the force. We do that for each of the 3 components, x, y, and z. We set up the initial positions of the x, y, and z vectors. We set up the initial velocities of the x, y, and z vectors. Or x, y, and z components, I should say. And then we'll output some graphics to make it look nice. So I'm going to go ahead and start with an initial x position of 1. And we're going to run this. And you can see we get an animation. And our animation doesn't look like it's doing anything. Why doesn't it look like it's doing anything? Well, it doesn't look like it's doing anything because the rest length was set at 1. So if we start at an equilibrium separation of 1, there's not going to be any force, there's not going to be any acceleration, it's just going to sit there looking at you. So we got to give a different value here. So I'm going to compress the spring a little bit. I'll change it from 1 to 0.95. And you should see that this will start off compressed and then expand and then contract and expand and contract. So if this worked correctly, the atom on the right-hand side here should be pushed out to start off with, and it is. Now it's a small amplitude of oscillation, so it's just moving a little bit. If I speed it up, you can see it going a little bit faster. Makes it a little bit more noticeable. So effectively what we've done is we've clamped down the atom on the left. We've left the atom on the right free, aside from the bond that's connecting it to the first atom. We're just letting it vibrate. And if we look at that motion, you can see it mostly looks like simple harmonic motion. It looks like this is a sine wave. So far, not really a whole lot of difference between our anharmonic potential, the Lennard-Jones potential, and the harmonic Hooke's law potential that we saw earlier. That's going to change. So remember, Hooke's law, we can approximate things as using a Taylor series to first order. So we can use a Hooke's law spring force if the deviation from equilibrium is small. So as long as we're close to a separation, that's the rest length of the bond, Hooke's law should work well. It should look like simple harmonic motion. But I don't have to get that far away. So I'm going to go, so remember the bond length is 1. I am going to now do a separation of 0.9, so only 0.1 away from the rest length. And you can see this is going to start to look a little bit different. It's subtle. See if you can see what's going on here. Goes boing and boing and boing, and it's hard to tell, but the compression happens faster than the or let me rephrase that. When it's compressed, it's moving and accelerating faster than when it's stretched. And you can see that more clearly in the plot of position versus time, or the plot of the bond length versus time. So when it's stretched, first of all, it stretches a lot more because the rest length is 1 here. So it starts compressed at 0.9, and that's as far as it's going to compress. But it stretches quite a bit more than that. So it only compresses about 0.1 units, but it stretches 0.4 units, 4 times as much. Also, it's much sharper when it's being compressed than when it's stretched out and being pulled back. So you've got a fast boing, and then it stretches, and then boing, and then stretches. This does not look like a sine function. I mean, it kind of does because it goes up and down, but sine functions do not have this discrepancy where it's much sharper on one side and much rounder on the other side. So this is one of the features that we're starting to see, is that as we get away from small deviations from equilibrium, it starts to look less and less like the simple harmonic motion that we started with. And in fact, we can make it look very not like simple harmonic motion if I compress it too much. So let's say I compress it down to 0.5, and I run that. So it's compressed. It's going to feel a force trying to push it out because the molecules are stuck too close together. They're going to feel a repulsive force, and boom! Yeah, that's not coming back. It's like there was a little mini explosion in my atom here. And you can see that even better again in the plot. There is no more restoring force here. That's going to be bringing you back. And if you recall, again from the Taylor series video, when we were talking about the Leonard-Jones potential, the Leonard-Jones potential is a much better model of a real spring or a real molecular bond, because if you stretch it too far, it'll break. Once you stretch it too far, you have no more force, no more restoring force trying to bring you back, which is exactly what happens in a molecular system. If I have two molecules that are really far apart from each other, they don't feel a force pulling them back together, which is not the case for the harmonic approximation. For Hooke's law, you always have some force unless you're at the equilibrium position. We're going to stop there since this video is getting a little bit long. But thank you so much for watching. Go ahead and like the video if you liked it. And if you'd like to see more of these, please click subscribe.